I can start now.
Okay, we can start. So our lections today is kind of ambitious, but we will just look at the basic of all of these Spanish words as that presented here. So let's start. What is actually GPU? What is the difference between CPU and GPU? CPU is one big it's a heart of computer, and it's calculated different stuff. ALU is green one box. It's just for example 4 core in a CPU, and they are calculating something, and you can see that a lot of different stuff in CPU also exist except of this ALU. So control unit is very big, and charge is also a very big part of CPU. But when we will see, when we look at GPU, it consists almost entire from ALU, and it almost doesn't have any charge and control units too. So this is a device for computing parallel things on a computer. And basically GPU is doing only this, and each ALU is really dumb. It can do anything except for example summing stuff. So basically ALU is doing shaders, and the reason why we have such big amount of these green boxes ALU, because the data that is passed to GPU is it's a lot of data, and it's all parallel, and commands, it's commands on this ALU is the same for every unit. So for example, we can send here, we can the CPU can make some data, so data points, and pass it to GPU, and GPU will start to compute something, and that is that you write in shader, for example. So each point is going to these green boxes. So, and GPU is starting to compute in all of this stuff for this data that is passed from CPU. And this is how it works in computer, and this is why GPU is such a device, such a specific device for computing parallel things. For example, this data can be can store coordinates of points, and for example, it will be a vertex stage with vertex shader, and each ALU will calculate somehow manipulate data around this point, for example, and it can calculate another position of a triangle, for example, or in another stage, in a shader stage, for example, is in vertex stage, for example, it can calculate already some colors, or make some textures. So this is how it works. So so here we can see how OpenGL 2.0 pipeline looks like. So we creating some buffers with points and passing it to we preparing it on CPU, of course. And here we can see two stages, vertex shader and fragment shader. It's called pixel shader here. And we can see how it works. So this data is passed to vertex shader. Vertex shader, what he's doing, he recalculating every point that you pass in the data through some rules, and there are later rasterization is happening, and the pixel shader shader is calculated, for example, colors, and later you can see all of this stuff on your device. It can be even a mobile phone. All of new mobile phones also have a GPU. Actually, it's not basic knowledge, but every mobile phone also have a GPU right now. It's a very sophisticated device. In our time, in 2K 2020. So what we have, for example, in GLSL shaders. So what is the difference in shaders between ordinary program, as you probably see already, maybe you saw it somewhere when you have some I don't know, loops, some variables in different languages, in Python, in C++, C#, JavaScript. And what is the difference between these kind of programs and the shaders? Basically, GLSL, it's a C-based language. It's looks like C. It's kind of, but it have special words. For example, GL position, GL point size, GL so whatever, GL color, and so we have free special special things in GLSL shaders that is unique to shaders. It's called attributes, uniforms, and varying. It's related to OpenGL shaders, especially these names can differ if it's different shaders. So the OpenGL shaders, they working everywhere. For example, macOS, direct Windows, and Linux, and but there are also actually another shaders I need to say to you. For example, on Windows we have a DirectX. It's used GLSL shaders is called. On macOS it's called Metal, and on Linux they have a Vulkan. Vulkan.
Question: is it true that Mac OS deprecated OpenGL?
Yes, this is true, and
what does it mean? It doesn't exist on Mac OS, or it's still there?
It's still there. It's working, but you probably can't program in OpenGL anymore on for new programs, for new applications.
But when I'm in the browser, for example, then I'm using WebGL. which is kind of
Everything
variation.
will works with WebGL, and it will works forever.
What's like WebGL and OpenGL? Are they related?
WebGL it's OpenGL 2. WebGL 1 is OpenGL 2. Basically, copy it entirely, and with only two maybe differences, that is related to transparency on the layers. That's all. So basically, WebGL is basically OpenGL 2.0. Yes, it's embedded system. OpenGL.
What's the latest OpenGL now?
OpenGL latest probably 5.0.
So it's
maybe
like an old version of OpenGL.
Yes, it's old version of OpenGL. Yes, but Web is creating a new specification. It's called WebGPU, and it will be kind of superset of Metal on and DirectX 11 and some kind of Vulkan. Vulkan also actually using GLSL inside. Vulkan you can use it on it's a system for Linux. It's shaders for Linux.
So just to understand, right, all these things that you're mentioning, they're API for interacting with GPU.
Yes, this is actually wired that different systems on different operation systems they using different shader languages. It's not obvious, and even you using, for example, C++ for every of this platform. Usually you don't have such a library that is common for every system, and if you making a game, it's nightmare to manipulate all of the shaders. That's why usually some people use it OpenGL because it's supported everywhere.
What if I use like a program, let's say like Notch or the Touch Designer or any of that sort? What kind of API do they use?
They're using GLSL, as I understand, and they don't work.
GLSL
Mac OS and on Linux. Am I right?
Touch Designer works on Mac.
Okay. So
and for Touch Designer, it's actually GLSL.
Unity works with HL.
Okay.
But Notch,
but Unity
Notch
actually
works with HLSL, but I don't know anyone who.
Unity you can run Unity.
Okay.
Yeah, it works.
Unity shaders on Metal on Mac OS because they're using kind of shader translations program special, and there are also special library called Shader C. It's on a GitHub. It consumes shaders in special format and then translate it to any language basically. And it's so you can use different shaders translations. Is for example, a shader C in GLSL is GLSL lang is this kind of library. You can find it into GitHub, and this is how a new WebGPU specification, for example, works. Worked at first, and then later. So if you will look at, for example, WebGPU specification, they started from these libraries, and then later they created shader translations by himself. Google make it, and also Firefox is created. Naga is another library that is translating So web GPU to basically any shader to any language, but I'm not sure about quality. So here, basically, what is the difference between all of them and why they so specific to shaders? So I want to describe it.
Those are the
properly.
data type you can pass to a shader.
Huh?
Are those the data type you can pass to a shader? Attributes, uniforms, and
Yes, attributes and uniforms you can pass to the shaders directly. This is attributes, you can pass it to your shader, and uniform you can pass it to from CPU, but varying it's a kind of internal thing. So what is the difference?
Why does attributes not go to fragment shader?
Attributes not go into fragment shader. Yes, this is true. Because
it's really annoying when when you're writing shaders and you want like this attribute in the fragment shader, you have to like pass it through this varying.
Yes, you should pass it through varying.
But is there like a reason why you can't just like access it?
Yeah, fragment just doesn't know about this anything. Fragment, okay, here we have a triangle. For example, I pass in attributes. So the attribute, each attribute is a coordinate. Coordinate, yes, it's a two-dimensional coordinate. So 0, 0. 2, 0 is x, y, x, y, x, y. And for example, we have a 6 here, 6 points, and attribute is here is just a two-dimensional point. So we pass it a buffer. It's kind of array of data here. So this array, and vertex shader will looks like so here the position attribute will be like looks like that. So basically vec2 a position and it for example 0 0 2 0 1 2 1 2 2 0 3 2. So here we can see so 6 points, and the first one is making one triangle and the second one is making another triangle. Everything in GPU is triangles, and because it's the simplest shape of a polygon, it's a polygon with the smallest amount of vertices.
I think it's flat.
And also it's flat, yes. It's always
3 points always form a plane.
yes, 3 points. Yes, these 3 points is also they making a plane, and then they making, for example, a normal. Yeah, and basically it's so how you, for example, between 2 points you can always make a line. Between 3 points you always can make a plane. So basically it's there are a term called coplanar. So yes, so 3 points it's kind of minimal thing. Yes, so we can draw all attributes around points. So attributes are the data that differs for all points. This is attributes. So you passing it to GPU from CPU. Uniforms at the same time. If you make a uniform, for example, time equal to 6, and it will be everywhere at this point in vertex shader. It will be everywhere 6, 6, 6, 6, because uniform here you can pass it to vertex shader, and also in fragment shader actually you can use it later. So what's happening with sort thing, what is varying actually is, so when a vertex stage is happening, you are recalculating all of this data. So you take in all of your attribute with position, you recalculate it somehow, and later on rasterization, for example, stage, when you calculated everything, and everything, so computers understand where your points is located. This is basically, actually, this is pipeline that is wired somehow in GPU, and this is a pipeline how all graphics happening. That's why you can't done it in another way. So it's works like that, and you can't do nothing.
So when I'm just in the browser loading a website with some CSS in it, and there is some like graphics rendering, like buttons and stuff, does it use
Yes.
the same pipeline?
Yes, yes. It uses, for example, 2 triangles for background. So here, basically the same, but it's square. So 2 triangles is making 2 triangles, or even one bigger triangle, but we can say it's 2 triangles, for example. And the background pictures is just a texture that is on background, and yes, it's working exactly the same. And each, for example, here we can see a font. Each font is also shader works right now on my computer, and everything is works exactly the same, exactly. So you can see CPU graphics maybe only in console when computer is starting to work. So when you see black screen and all of this graphics is that is with not good quality, this is done on a CPU. But later, when you have all of the fancy graphics with when your fonts is really clean and really good, and everything is on a GPU. Yeah. So it is clear actually what is the difference between attributes, uniforms, and varying. And I'm not saying actually about varying, so I need to say about this too. So what's happening between vertex shader and fragment shader? Fragment shader, it's he takes all of the triangles, all of the that you calculated in a vertex shader, and started to fill it with pixels. So here we have a pixel. Here, for example, we have a square, and rasterization will happen. And for each point, it will begin from the start. And this GPU is later will calculate each pixel of your screen, basically. So each allo will calculate another pixel. If on a vertex stage each allo calculating one point, next point of triangle. So it's taking point and later making some primitives. Yeah. So the fragment shader is calculating each pixels. So, and actually it's interesting that there are some. Okay. So we need to explain what is varying actually is here. Maybe we should go to another stage. So, and to explain.
Will you show how it works?
Huh?
Will you show how it works? Like we get vertices,
You can show some
color
examples.
them.
Yeah, we can actually open a code pen, for example.
Like,
Let's start with that.
First, let's do theory.
What? What?
Let's do practice.
Yeah, first
theory, then.
First theory, then practice.
Yeah. So varying is happening here. It's interpolating some data. So varying, why is they call it like that? Because it's wired into GPU, and varying always interpolating data between points. So on a fragment shader don't know about points at all. If a vertex shader, for example, doesn't know about pixels, about points, about, I don't know, what can happen here is some texturing. In vertex shader only know about points, about about triangles. Sometimes you can see indexes here. You can pass, for example, instead of this data, you can see 0. You can see it is repeating, yes. So 0, 0, 2, 0. So this is 2 is repeating. This is 2 also repeating. You can pass here actually 4 data, only 4. 0, 2, 0, 1, 2, 3, 2, only 4. And then say to GPU that you can you should take here first, and you can make another buffer with indexes. For example, and it will be 6 indexes already, so it should be 6 anyway. And you can say it on the first index we take in from here the coordinate, on the second from here, on this it's kind of, and the fourth, for example, you can say it that you take in 2 from here, and here you can take from here. And so basically, yes, it will be the same. So we can see attribute uniform and varying here. Uniform is the same here and here. It's kind of in a shared memory. It's located here in red part. Attribute, it is what you, it's points that you pass. So vec2, because we have 2D graphics here, and here how it looks like, for example, vertex shader, and here is a fragment shader. This is the simplest example of all graphics. So it's kind of simple when you see it on shaders, but when you look at CPU, it's nightmare actually. So this small example, it's 100 lines of code in JavaScript, for example. In C++, the same, basically. Maybe you can, in Python, you can use, for example, some library. Maybe actually in JavaScript also you can use some library that is already prepared all data for you. So you will not use so it will be not so verbose for you. Yeah, you can use some libraries. It will be helpful even for such kind of simple program. Yeah. So what we have here, we have a matrix that is common for vertex and for fragment shader, that is in Chach. So we have attribute that is just an array that passes to GPU, and we have this varying, and that is calculated on the rasterization part. When vertex shader calculate all the data of points, it will start to pass through all and so the picture, when picture is appearing on the screen, it's like a printer, like an old-fashioned printer that is printing each pixel on your screen line by line. So it's going like that. It's going like that here. Just we have a pixel here. This pixel is related to this triangle. Okay, how to take this? We have a fragment shader. Okay, this is a fragment of a triangle. We have a fragment here. So varying, what the fuck is it? Okay, on the previous stage here, we make a rule for this varying, for varying color. We say that it's will calculate like a position, so multiply by half and then edit another half. So it's just like that. So yes, we calculated everything. We have a blue color here. Okay, next the same, another color. So and another line we will take. And
why is it blue?
it's blue just because actually.
But there's some calculation.
We have a matrix here.
In
this kind of black black it's a black box that can consist anything here, anything there, and it's mat free is 3 by 3. It's 8 or it's 9 actually coefficient that is multiplied on this. And when we calculating this, it's become some kind of for example, if v from -1 to 1, when we calculate when we multiply it by 0.5 and we'll add 0.5, we will have from 0 to 1. So each color will be valid from 0 to 1. And at some point, for some reason, for this we have so x is here, and y, so y is up, yes, and y is second. So RGP, G is 1 here. So G is blue, G is so we have RGB. So red, green, blue. Yes. So it should be kind of green. So we can see it's kind of green. Yes. But because blue, it's z coordinate, and z coordinate can be any here. I suppose that z is here around 1, and this is why we have ocean color here. And
So-
because it's green and blue at the same time.
Blue is neutral color, and it's for the z-axis.
No, it's here. We have z is around 1. It's just because we have such kind of matrix here. If we want to look at the coordinates here, we can.
Maybe we can go to the float 10.
Yeah, we can actually go, for example, to shader toy. And we can create a new one.
Can you make it bigger a little bit?
Can you make the font a little bigger?
So
Can you
this-
scale the window? Just Command plus. No more.
Oh, thank you. So here we see, so red, so R and G, we have R and G is passed here. So, but we can, for example, make it Z to 1, and it will be like that. So we can see a lot of blue here, a lot of ocean color, blue color, and the pink color and white. So basically the gradient is so.
Yeah, it's like we added blue to basic UV.
Huh?
Before it was like basic UV picture, UV coordinates, like red to red and green, and now it's mixed with blue.
Yeah, it's the same actually, but because we have two-dimensional, so UV, it's here. It means that it's actually kind of attribute here that is so. I'm just a little bit confused how we go here from the triangle. So basically what we have here and what we have here, it's almost the same. So when we open a shader toy, we play with fragment shader here. So
Fragments mean pixels, right?
yes, so pixels, and the vertex shader is here always the same, and vertex shader is just to have a quad. It's called quad.
So vertex shader is like geometry.
Yeah.
Yeah, geometry is just a square, and that's why also in all post-processing geometry is always a square. Also in notch, for example, in the geometry always like a square. Yeah, just a quad. So when you making something on shader toy, when you making something in Touch Designer in Notch, you usually operating with the fragment shader, and you kind of pixel wizard here, and you making everything with pixels. So you doesn't care about fragment or about vertex.
Sometimes
shader
you
here.
do. I guess like I think about it. If you want to do anything with color, but it's keeping the same shape, you do fragment. If you want to displace existing shape, let's say I have a sphere, I want to like form.
Yes.
Then I do a vertex
Yes.
shader, right?
Yeah.
I can-
If you in Touch Designer and you are trying to replace and trying to displace vertices.
Yeah.
Yes, you're using vertex shader. Yes, yeah, for sure.
At which stage is normal calculation is applied?
Normal calculation.
Yeah.
What
I
normal?
guess normals have passed to the shader as one of those.
Normals is I will show you. Normals it's just an attribute here. So the thing is that you have a normal. The thing is that you can't pass any data except these two to the shader.
And normal is an attribute, uniform or varying?
Normal is not uniform because normal is different for each points, but
So it's attribute.
it is attribute, yes. Normals, when you send in a normals for each triangle, it's passed through attributes, but because because attributes is so stupid and pipeline is so stupid in OpenGL, you pass in the same data for each triangle. For example, this triangle we have, and we pass in here normal, here normal, here normal, the same for this triangle, because the normal for 3 points is one normal. And for
Can you show what normal is in the browser? Maybe people who are not familiar, there's some
There's actually like multiple types of normals. There's polygon, vertex normals, how they connect to each other. There's like 3 different normals.
True in software, but I guess in the OpenGL level, what he's saying is essentially always like per
Only one
point.
polygon
Yeah,
normal.
yeah.
Not vertex
No, not
normals.
polygon. He's saying it's per point. It's only a point normal.
No, unless if you use the index approach that he was talking about, like you don't repeat points, then you can give one normal.
No.
So basically,
I'm not sure
I just
about-
wanted. I was just. wondering-
maybe yes.
No, if you use the index approach, then
Yes,
you only need
but you
one.
need the index not only for points but also for normals. Yes?
It's the same. It would be the same. Like the index would correspond to the point
If
array
it's-
and every other array.
If
then
it is the same, but so it will be repeated. If index is the same for triangle, it will be repeated anyway. So if index approach, yes, you can use it index approach, but for normals, I'm not sure that you can use another indexes for normals.
No, it's the same index.
So it will be repeated. You can.
Anyway, we
no.
don't have to
No,
go
you-
into technicalities.
So basically, here are the normals.
the normals is just a perpendicular vectors
So
usually, right?
I
to
hope
the surface.
everyone is understand what is normal. So here each square is actually 2 triangles. It's kind of I'm not sure that the pictures is correct. Maybe here is a little bit better, but it's the same. Well, here we have a triangle. So with one normal, and attribute will be for all of these 3 points the same with this normal.
So what if I'm usually normals are just an attribute on the geometry. So if I have a 3D model on OBJ format, right, I have some data representing the normal, which is a vector, right, which is the 3 value. But sometimes I might not have that in my 3D model, right?
Again,
If like sometimes I usually have models. Let's say I made the sphere in Blender, right?
okay.
And then Blender, I can compute normals and define how my surface looks. Like this one, it's very jaggedy, but I can make it smooth with.
Actually,
normals,
yes.
right?
There are special normals.
But my question
this-
is, what if I don't have normals? What will OpenGL will do in this situation?
If you don't have normals, you can calculate normals. It's actually easy for.
And I guess Isaac asked,
for-
at what
for
stage
each-
is normals calculated?
Yeah, on vertex or fragment shader?
Normals is calculated on CPU,
Oh, okay.
Oh,
Not
so-
in the shader itself.
not in the shader. Normals is just attribute. and it's
Are
just
they
an attribute on vertices.
Is it calculated before this pipeline or for
Before.
every frame?
And normal can be actually be not the same for each points of triangles, like I said at the beginning. It can be on a vertices, and it can be differ. It's kind of so the normal here it's it can be kind of average of these two. It can, for example, here we can see 4 planes that is connected to these vertices, and because each vertices is stored information about normal, you can store in for these triangles the same averaged normal, and it will kind of it will be not as flat graphics like here. It can be smooth, yes, and if you can place normals like that, and in the end you will see smooth picture on the screen, because with all of this varying that will be here, because you will have here one normal, here another normal, here another normal, and it's normal that is connected to another shapes. That's why normal will be not the same for all of these points in triangle. It will be continuously floating from one normal to another normal. It will be interpolated from one normal to another normal. That's why it will be shading. It's called it will be basic shading.
That's right, shading with pencil.
Lambert.
Lambert is the guy who invented this shading model.
He's a person.
Yeah, he's a person.
Fong is also a person.
Yeah.
Fong, oh yes, but Fong is better than Lambert actually. Yeah.
The
It's
standard person.
it's kind of I think here. Where is? Maybe it's called Guard.
Burley, he's not.
Go right. Either. So I want a picture when I maybe. Yeah, I think here. So we can see actually it is the same picture. In the first picture, in attribute normals, I will everything is clear actually, and nobody is lost with this our information that we are talking about. So we talked about
everybody's lost.
Huh?
Everybody's lost.
Everybody is lost.
Yeah.
I maybe don't understand if how point can have a normal, because only plane have a normal, I think.
True. Yeah.
How point can have a normal?
How vertex have
Yes.
a normal, because normal it's a plane attribute.
You just place it and from a CPU on a CPU part.
Well, you can. I guess you can calculate based on adjacent vertices. Like if I have
You place in
a
here
plane.
any information. You can store, for example, here.
But an arbitrary, yeah. Normal is an arbitrary vector.
You can store here colors, for example.
It's not necessarily
You can
perpendicular.
store here normals. You can store even matrices on each point, because we have attributes, and we have this kind of pipeline, and it's pretty done, and it's work like that every time. And you can place here in these vertices some normals.
Okay.
And normal is just a vector. So like
Normal,
Yeah.
each of
normal
them-
is just 3 points actually. Yes,
So
it's,
like
it's a
if-
vector. It's 3 points.
Okay, we have one plane and second plane, and this normal is not this normal, and 2 points connected to this plane, two planes,
Yes.
and which normals will be in these vertices?
Yeah.
Not this.
Which normal will be, for example,
V3 or V4.
V3 or V4?
V3 or V2.
I think the answer is. I think what he's saying, it depends, because normal is or arbitrary vector. So when you're making your sphere in geometry in Blender you can like say, oh, smooth normals, or you can even like pick a brush and start combing the normals. So basically, like they like hair on the surface, and you can like create like a weird shading kind of effect. And then when you save to OBJ file, you have, if you open OBJ file in the text editor, you will see the normals stored there as 3 value vectors essentially. And then when they they got passed as an attribute to this like rasterization pipeline. But I guess when you don't have normals, they calculate it on the CPU, right? You say,
Yes.
and that probably depends on the like environment you're in. If you're in the
Well,
browser, maybe you calculate in one way. Maybe in Unity they calculate it some other way.
But I think it's simpler than that. They're just like two, like if you pick the one corresponding to the separate triangles, then the shading will look flat. Like, you know, you'll be able to see every triangle.
Like this one, right? This
Yeah.
example you showed.
Yeah, it'll
Like
look
first
like
one?
that
Yeah,
this
yeah.
one. But then if you choose to like average,
What? Yes,
if you
yes,
use
yes.
an average,
If-
then it'll look like the smooth one.
But here, for example, we have 2 triangles, and these 2 triangles they have 6 points, and they all have the same normal that is located here. Chick.
Okay.
So when 2 triangles
but-
connect,
But here we averaging in all of these points. We averaging between all of them, and we have already here another picture.
So there is kind of smoothing function.
Yeah. In Blender, it's
It's-
called
it's-
shade smooth.
It's in Blender. In Blender, you can recalculate instead of flat shading, you smoothing shading for normals you making, and you will have this kind of picture. It's
more like on the right maybe. This is, I'm not sure this is
maybe
God
yes,
or-
maybe
I
yes.
never actually heard about this one in the middle.
This
Looks weird.
yes, this looks weird. I don't know.
I think it's deprecated for most
Yes.
3D softwares.
Yes, it's already
I think
so.
even phone is deprecated.
Huh?
Isn't it?
No,
Font-
font is commonly
font-
usable, yeah.
Font,
And Cinema 4D, I guess
uh,
it's the main
Hmm.
normal comparison.
Font model is actually more deep. It's related to light, and
All of them related to
even
that.
if you making, for example, tracing, sometimes they using font model in one small points, and because you passing a lot of rays, that's why font model making a good picture. What is it? Okay. So where we stopped? think here. So I think we understand how wiring is working. But at least on a normal, we understand it, I think. But we can repeat it here for colors, for example. We have a color, so what is doing the color here? On a vertex stage, I will repeat it again, what's happening here. Each point we pass in here to vertex shader. We have 3 points here. 3 points with 2 coordinates. So that's why A position should have 6 data. Uniform should have 9 data because it's a matrix 3 by 3. It's 3 point, 3, no, it's 9 coordinates. And this is not passed through CPU. It's calculated through a graphic pipeline. For each points, for each arbitrary point into exact triangle, V color is calculated by this formula. So yes, when vertex shader is calculated, so it's so we have this rule to how to calculate the varying. So when the fragment shader is going for each point, for each pixel on the screen, it's be calculated very simple. The fragment shader is very simple here. Just taking the color and place it in this pixel. That's all. Really simple example. We can open it. I think.
Finally, we opening it.
That's the fun begin.
And it's looking different. And it's looking different.
Yes, exactly, because I'm changing it. And because the vertex shader, I'm changing it. So
You didn't like the green color?
yeah, I just a little bit changed it.
And so this is in WebGL context, right?
Yes. What's happened?
Munrocket.
Yeah.
Semicolon and then
Quotes?
oh, the bracket maybe extra. Nope, it's fine.
I think it's missing quotes.
Like what? No.
It needs quotes and oh no, this is the type shading.
Oh.
Just undo it, it was working.
So maybe we can open. We can open it. Here. Actually, I know what to do here, and we can just do like that. Oh, okay. And it will be the same. So yeah, it looks like the same. Yes.
How are you doing this scaling and stuff?
So it's a matrix here. So matrix. I am just calculating matrix, and it's not my actually code. I just take it. Yeah. But what it is doing is making special matrix to move it and to rotate it and to scale it. So this is we changing uniform here the matrix. So we can remove matrix here too, just easily, like that. And look what will happen. Whoa!
Nice.
So it's big. Okay, if it's big, we can.
So basically, took the entire canvas.
Oh, we
Bigger
can.
than the canvas.
This is bigger the canvas, yes.
Still big.
Interesting.
So even a triangle at all.
Yes, it's okay enough. Just very big. So we can see the data that is passed here. So the data, we can guess what the data is passed by these triangles. Yeah. So somehow like that. We can find it in the code, what data is passed here. But we can guess actually too. So somehow like that. And what to say here more? We can play with this code. We can change the color. So each color here, it can be. We can pass actually a color like an attribute. Or we can pass, for example, a normal to each vertices and take it like a color, because normal is also a color. Yeah, it's 3 points. 3 points of normal. You can use it like a color. So that's why we have this kind of picture. Wait. Wait, sorry. Oh, these pictures. Yeah. It looks like that.
Great colors.
Oh, somehow like that. Yes. So this is an example. Let's go further. So finally, we can maybe go later, or we'll go next. Yeah. So I think we talk about everything here. We not talk about only texturing. Actually, if we will add here things like oh, not sure that I can type here or anything, and here is broken too. So yeah, here for example, in the fragment shader, here we can say special words for texturing, and we can start to take texturing here. But maybe it's better to show it in shader toy. So at this point we can go to shader toy pretty easily, because shader toy, it's as we said already, it's just a fragment stage, so it's perfectly fit for us if we want to read some texture, for example. Texture. It's okay. Okay.
What's this A channel to?
What
is this I channel? Where is this texture coming from?
What here at the bottom.
Oh.
So actually, I'm not mentioning that. So here, for example, texture. It's we can choose it. So we have different textures predefined here. So yeah, we just making for example a variable C, its color, and making texture. So we put in the name of the texture here that is patted through uniforms. Here we have a uniforms in shader toy. So shader toy have uniform time. It's here time. Resolution. It's here. And mouse. It's the the most frequent one. So we can, for example, add here time, and we see that texture is read it not from UV, because UV is
what will be if you multiply it by 2? UV multiplied by 2.
UV multiplied by 2. It will be and just bigger texture. Basics. Something like that. So you can make a sound here, and it will go back and forth. Also, we can do anything here actually. So we go into kind of next stage of our lecture. I think we should make a break here.
Yeah. So there's wine here if anybody wants.
Yeah, you just need a cup.
Because the next part will be really hardcore.
Hardcore?
Yes.
Like this one was not hardcore.
This wasn't hardcore?
No, not enough.
No?
Yeah, but at least for someone, this part was already familiar for some people. But next part will be not familiar to anyone.
Even
So-
for you?
No. For anyone maybe. Maybe somebody.
SDF.
Yes. No,
That's
for you maybe.
That's a wormhole.
Yes.
Never. I have experimented with SDF, but nothing can get into production because for me it's like,
Yeah.
I can make blobs, some kind of metabolic,
Yeah.
but that's all.
Yes, it's a rabbit hole. Yes, I agree with you.
Can you make faces with SDF? Can you make faces with
Actually,
Yes,
you
why
can
not?
find a photorealistic picture. No, not photorealistic, Pixar-looking picture
Yeah.
made completely with SDF.
No,
it's possible.
I know you can. I mean, like, can you?
Yes.
Can you?
Why not?
Yes, you can. Cool.
No. Nie, nie znam tego.
I have